Hi, I'm Baekjin Kim. Today I'm presenting the joint work with Ambuj Tewari. The title is Randomized Exploration for Non-Stationary Stochastic Linear Bandit. As a warm-up, I would briefly study stationary stochastic linear bandit and several existing results. In a round T, a learner chooses an action from action set and observe a reward yt, which is inner product between action and fixed true parameter theta star with additive sub-Gaussian noise. We also denote the best action xt star, and as a measure of evaluating a learner, the expected regret is defined as difference between reward the learner would have received if he played the best in hindsight and actual cumulative reward. Two standard solution in this setting is linear UCB and linear Thompson sampling. Based on optimism, linear UCB maximize upper confidence bound for expected reward with confidence level A, and it is deterministic and achieve minimax optimal regret bound. However, linear Thompson sampling is a randomized algorithm that maximizes the expected reward given theta tilde sampled from posterior distribution, and it achieves regret bound with extra square root d order. Once action set is large or infinite, then linear UCB cannot be efficiently implemented since the spectral norm of each action should be computed before maximizing it. However, linear Thompson sampling can rely on offline optimization oracle so that it is efficiently computable. So randomization in algorithm allows itself to achieve empirically better performance or oracle efficiency. One perturbation scheme is to replace optimism in linear UCB by simple randomization so that the randomized linear UCB algorithm can be constructed by replacing confidence level A with random perturbation Z of t. The other perturbation scheme is to perturb estimate before maximizing the expected reward. If Gaussian posterior is considered, Gaussian posterior can be decomposed into least square estimator part and additive Gaussian random vector part. Interestingly, it is equivalent to randomized linear UCB with decoupled random confidence level C of t, x. So, four different algorithms are reported in the table in terms of the regret bounds, randomness, and oracle access. So randomized linear UCB is minimax optimal, but not oracle efficient. However, Gaussian linear Thompson sampling is oracle efficient, but slightly suboptimal. Using two perturbation scheme, now we move to non-stationary stochastic linear bandit. The main difference from stationary setting is that the reward is linearly generated from unknown time-varying parameter theta t star. This non-stationary consumption allows this theta t star to be time variant with total variation budget b of t. To gracefully accommodate time variation of environment, least square estimator should be replaced by weighted least square estimator with exponentially discounting factor gamma. Gamma should be between 0 and 1, and additionally we should define W tilde and Vt. The following theorem provides the high probability confidence ellipsoid for weighted least square estimator. And naturally, it provides discounted linear UCB algorithm, which is optimism-based and deterministic algorithm. However, optimism-based algorithm often struggles with conservatism in practice due to too large confidence bound. So the first randomized algorithm we proposed is discounted randomized linear UCB, which can be constructed by replacing optimism with simple randomization. The discounted randomized linear UCB is described as follows by obtaining UCB term and then maximizing it over action space. The second randomized exploration method is discounted linear Thompson sampling. It directly adds Gaussian random vector to estimate before maximization step. The discounted linear Thompson sampling is described as follows. Due to this direct perturbation step, it can have an access to offline optimization oracle so that its implementation is oracle efficient. The expected dynamic regret can be decomposed into surrogate regret term and bias term arising from total variation. To bound the first term, we define three events: weighted, least square, concentration, and anti-concentration events. The first event is that weighted least square confidence ellipsoid contains surrogate parameter with high probability. The following events are concentration and anti-concentration between perturbed expected reward and expected reward. And the general algorithm we would like to analyze is to maximize the perturbed expected reward ft tilde over action space. If first two events hold with high probability and anti-concentration event hold with non-zero probability, then the expected dynamic regret of this general algorithm can be bounded by the following. As corollary, dynamic regret bounds for discounted randomized linear UCB and discounted linear Thompson sampling are reported in the table with regard to dynamic regret, randomness, and oracle access. We would like to highlight the statistical optimality versus computational efficiency trade-off between two randomized algorithms, in that the former one asymptotically achieves the optimal dynamic regret, but the latter one is oracle efficient but have an extra logarithmic factor in k compared to the minimax optimal regret. We ran simulation study using a sample of 30 days of critical live traffic data. We construct two linear models, and the model switch occurs and at time 4,000 out of 10,000 time horizon. We run and compare the 5 different algorithms. As a result, first, two randomized algorithms, discounted randomized linear UCB and discounted linear Thompson sampling, outperform discounted linear UCB in every scenario. Also, discounted linear Thompson sampling works better than discounted randomized linear UCB in all scenarios and perform as well as linear Thompson sampling with oracle restart when action space is large and dimension is high, as figure E and F. Also, secondly, discounted linear UCB works better than linear Thompson sampling only if low dimension and small action space are considered. Otherwise, it performs worse than the linear Thompson sampling, which is originally designed for stationary environment. The poor performance of this algorithm is due to its conservative confidence bound, so that the conservatism issue can be partially tackled by two perturbation scheme. Thank you.